Three facts to start off with. First, in the speaker's lounge, there were mimosas. So I apologize. I'm kidding. I had nothing to drink this morning. Second, I am jet lagged. So that brings about the third fact. I used a lot of pictures in this. You're all going to be witnessing a lot of detailed informational slides throughout the next couple days. So I thought that I would talk to the themes around the edge, and as we drive into the panel, I wanted, and most of the brilliance of driverless cars and ubiquitous Zettastructures, which I could not wrap my head around until George just came up this morning and talked about Zettastructures in the form of traffic, and I think that's really interesting, data working backwards from geography. So jumping right into that, since we have 20 minutes, I want to talk a little bit about data gravity and the post-5G edge. Now, you might ask what data gravity is, and we will definitely get to that. But I think it's important to note that there is a convergence coming, a big convergence of the wireless world as well as the wireline world. And I'll go a little bit into my background and say that I've been working in data centers for 25 years. If you're from the US and you have been in this industry for a long time, you might remember co-location companies being called application service providers at one time. And my companies owned lots of floor space in ASPs, where I spent a lot of time racking and stacking infrastructure. But I also happen to be telco. And I predict, I don't think I'm on the big ideas panel tomorrow, but I just wanted to make a quick prediction that in the next 5 years' time, half of you will be telco. Half of you will be telco-based, and half of you will be data center-based, and these worlds are colliding. And I want to talk a little bit about that. So I don't know how to progress here. This is not the mimosas or the jet lag. I literally cannot move forward, George. There we go. So, one of my favorite authors, Hunter S. Thompson. There's no honest way to explain the edge because the only people who really know where it is are the ones who've gone over. And you might think of this as drinking the Kool-Aid, and we definitely have. But I've got a physics background, and one of the things that I was privileged enough to do in my career was work on May East and May West. Now, what's interesting about May East and May West, in the very earliest form of the internet in the United States, when UUNet and MCI and a bunch of fiber companies got together, does anybody know May East and May West? Do you know this? So not a ton of people. This is literally the backbone of the information superhighway in the United States. And if you may know what May East and May West is, but you may not know what it stands for, which is really interesting. Metropolitan Area Exchange. Now that's really fascinating, because when I think of metropolitan, I don't think of the entire United States. I think of an area. I think of a geographic, a more localized area. Now, that being said, today the internet that we've built, all of the data centers that collectively have been built in this room by lots of brick and mortar companies, lots of cloud companies, lots of CSPs. It takes a lot of different types of skill sets to build data centers, and I think that's both good and bad for a number of reasons, but we're also seeing a convergence happening here. But we're all, literally at the end of the day, we're all either manipulating atoms or we're manipulating bits. And that's really fascinating to think about. We're either bending sheet metal and creating HVAC systems and deploying physical infrastructure, or we're manipulating the code and we're manipulating the software that enables that infrastructure to deliver the experiences that we present to our consumers. Now, that internet is a very static internet. Save for your phone or your SIM card-enabled iPad or Microsoft Surface, the internet is pretty darn static today. I mean, it's dynamic in that we can get different data, but with regard to how we're getting that data, if you're a networking person, you advertise a BGP route, Border Gateway Protocol route, and you travel the information superhighway, and you travel it back, and you pretty much get this sticky bit that tells you that you're going to take the same roads. And I like the roads of driverless cars and serverless data centers, or Zettastructures. Now, I like the concept of ubiquitous Zettastructures as a plural, because if you take May East and May West in the United States, there is literally not enough glass, fiber. There's not enough glass in the ground in the United States to solve for the 175 zettabytes that'll be here by 2025. Literally, the pipes break. Secondly, next slide. Data is becoming increasingly localized and far more dynamic. I like the driverless cars concept because today it's a supercomputer. I mean, the driverless car today is the supercomputer or the mainframe, right, of the 70s. We think that autonomy is going to be solved by all of this localized processing power. Just like we thought, when NASA was buying mainframes to solve for the mathematical equations to get a man into space and back, that mainframes would be the way we did this. Now we know, you just heard Suresh talk about how much land they own versus how much land they lease and where those locations are. Now we know that you can't just put one huge computer in one big building and solve for everything. We have moved from sort of at least in the IT level, from this vertically integrated supercomputer into a decentralized, commoditized, highly available, resilient type of environment. And I predict that in the future, the car looks more like a mobile phone. The car will have mobility associated, because of course there's tires on it, so it does move. But the connections, the infrastructure to vehicle, the vehicle to infrastructure, the communications, the car becomes the server, the road becomes the rack, and the city that it's in becomes the data center. And that is a far more localized internet. There is no need for that car to advertise IP addresses or DNS requests to someplace in China, if it's in Boston or Pittsburgh or San Francisco. Just like an autonomous car in Shanghai has no need to advertise its public addresses to somebody in Colorado or Texas. So what we're going to see, and there's a number of technologies coming out that are going to enable this, and they're going to sound crazy to you. This is one of my favorite authors. This is Arthur C. Clarke. And he says, if what I say now seems to be very reasonable, then I have failed completely. Only if what I tell appears absolutely unreasonable have we any chance of visualizing the future as it really will happen. And this is an interesting quote because as humans, we always get the value proposition wrong. We come up with great tech, we come up with wonderful tech, and then we leave it really to the next generation to go and innovate against that tech. We think that all of this next generation 5G architecture and mobile edge computing, et cetera, is for low latency applications and end user termination, et cetera. But chances are, sure, some of that happens, but there are some high school student or some middle school student right now, the next Bill Gates, the next Mark Zuckerberg is sitting in his room or her room studying, and they will actually define what these new capabilities will do. But what we know for a fact is that when you have 40 billion connected devices and you've got 175 zettabytes of data on the planet, that you have this thing called data gravity. You have data mass, you have application mass, you have the number of requests per second over latency in seconds plus the average request size in megabytes divided by the bandwidth in megabytes per second squared. Now, thank you. Thank you. This is what I call data gravity. I'll send you the slides, Peter. Now, at the same time, you have this universal speed limit in the form of 186,000 miles per second, and I'm very sorry. The conversion of that to kilometers for the Brits in the room, I can't do that. Yeah, fine. Miles works here. Fine. But what we do know is that if we're going to solve for the experiences that we're promising the next generation of users, consumers of autonomous cars. So think about this. A car traveling at 60 miles an hour travels a third of a football field, and I mean US football field, every second. That's pretty fast. Now, when you look at the car's requirements to deliver a 4-5 millisecond round-trip response time for somebody that might be registered on their phone as a human, and a caller that registers a pet as a pet, you have a sub-5 millisecond decision to make. You've got artificial intelligence, you've got machine learning, and you've got angles that LiDAR doesn't solve for. You have hills with obstructions that doesn't solve for all of that supercomputing to be held there. So now you need to place massive amounts of GPUs or TPUs, ASICs, FPGAs, lots of decentralized machine learning, lots of artificial intelligence very close to that car, so that car can get to its data center and back to that car within 4 milliseconds. Now, I've got 5 minutes. Let's look at AR/VR as another application. We'll talk about all these things on the panel as well. Let's look at AR/VR really quick. The human eye can see about 150 degrees horizontally and about 180 degrees vertically. And you can see 200 points at every degree. If you take some very mild compression, still capable of delivering a 4K-ish experience, you are generating 5.4 gigabits of data per second per eye. Now, your inner ear is responsible for your balance, and it's what causes you to get sick on railroads. If you are experiencing anything north of a 7 millisecond round-trip experience in VR, you will get physically ill. So if we're going to solve for these experiences like AR and VR and autonomous driving, we're going to have to re-architect the internet. And that is not hyperbole. That is something that we're going to have to do. If you remember Sun Microsystems, I had the pleasure of having Andy Bechtolsheim, the creator of Sun, which, by the way, just fun fact, Stanford University Networks, if you didn't know. But I got the pleasure of serving under Andy Bechtolsheim for a little bit of time, and he had a subordinate named John Gage who said the network is the computer. He said the network is the computer. Well, what is the network? Right? Well, is it licensed spectrum? Well, we certainly, I guess with 3 minutes left, how many people use the internet more on their mobile device than they do on anything else now? Most everybody, right? Most everybody, because we're at work, we're on our phones, there's no corporate firewall on your phone, you can get to whatever website you want. So this is called licensed spectrum. We use licensed spectrum. I'm not accusing you of doing anything with your phones. You've got 3.5 gigahertz, which is the community broadband. That's unlicensed spectrum. You've got 60 gigahertz, also unlicensed, different application, more for data ingress and egress than for telemetry. And then you've got your wide area networks, your metropolitan area networks, your campus area networks, your local area networks, et cetera. So the question really becomes, what is the network? And when we do the panel here, after Jim speaks, we'll talk a lot about what the network actually is. Now, with 1 minute and a half remaining, I want to talk a little bit about fixed fortifications being the monument to the stupidity of man. This is General George S. Patton. We build our data centers today with fault tolerance. And fault tolerance is great, but it's exactly like building the mainframe. It's having redundant everything. Well, when we're building cloud-native applications, and soon to be what I call edge-native applications, what changes? And when you go from 4 physical locations to having to solve for what we solve for, 40,000 physical locations in the United States. How do you do that with humans? Don't trust robots. But humans don't scale well with this type of management, so you have to write code. You have to write artificial intelligence. And this means that we have to re-architect the internet. This means the internet as we know it is completely broken. It will not scale for the types of things that we'll be building over the next 10 years. You're seeing lots of country to country, continent to continent, macro level re-architecting of the internet, but you're also going to see a miniaturization of a far more localized internet where you will literally be building wireless mesh networks point to point, created through lots of interesting technologies. Just chew on this for a minute. How many people know Bitcoin, cryptocurrency? How many people know the underlying technology of Bitcoin as blockchain? Imagine blockchain as a routing protocol. Just think about that. Imagine blockchain as a routing protocol, decentralized, point to point, and very low latency. If you don't have the proof of trust, if you don't need the proof of work, double commit that the blockchain has today, imagine what could be done with that. I'll leave you with this. We build our data centers to fault tolerance. We build our applications to be highly available. But what happens at the edge? What happens, is this fault tolerance or is this highly available? And I'll scale it. What happens when you're running a distributed application that has presence in lots of locations? Is this fault tolerance or is this highly available? So I'm very excited about the partnership that George has with, and DCD has with Uptime. You're going to be seeing some work done in this field. It's very, very fascinating work. We are trying to build the internet of tomorrow, and this is the group of people doing it. I say this at every DCD show. This is the group doing that work, so I applaud you. I'm going to stop, but before I do, make sure that you go to slido, slido.com. If you want to ask questions for the panelists or any of the speakers that you've heard this morning. And thanks.